Thanks, Charles. All yours.
Brilliant. Thanks, Ayush, for that wonderful introduction, and thanks for all coming along. So I'm Charles. I'm from DeepMind, and today I'm going to talk to you about memory in reinforcement learning. So my ambitious agenda is in 4 parts. First, I want to talk about Markov decision processes and all the stuff around that. That will sort of motivate us to then look at coverage and exploration and how we can learn to rapidly explore various environments. That will lead us to think about what is state and think about how we can form new kinds of states. So here we'll look at from egocentric experience, how we can extract allocentric memories of that experience and how that's useful. And then to sort of at the end of it, towards the end of the talk, we'll sort of summarize it all with thinking about what kind of tasks will require memory and what kind of agents can demonstrate those different kinds of memory. Okay, but first let's think about the problem we're looking at. And by the way, feel free to interrupt with questions, as they arise. That always makes things more interactive and quite fun. So this is what we're trying to do. We've got the usual RL setup. So if you're not familiar with it, here's a brief summary. We have a policy or an agent, and it issues actions to an environment. You can think of this environment as a game or something like that. And then in response to the actions, the environment sends back states and rewards to the agent. And the agent should pick this sequence of actions such that the rewards it gets over some period of time are maximized. And in particular, in this talk, we'll be thinking about sequences of interactions in an environment we grouped into episodes. So there'll be short sequences. You can think of this like if you're playing a video game, at some point the video game will end, like you'll run out of lives or something like this, and then you'll start again. And that's exactly the setup we'll have for our agents here. So one way, the common way to formalize this kind of setup is to think about a Markov decision process. And a Markov decision process has 5 components. It has a set of actions that can be sent from the agent to the environment. There's a set of states that the agent can move between. You have this transition distribution, and this transition distribution says, given you're in this state and you take this action, what's the distribution of the states you end up in? Then you'll have a reward function, which says, given you're in a state and you take some action, what reward do you get? And finally, there's a discount factor. And the discount factor tells you roughly how soon you should get rewards. So to some extent, the discount factor says, discount factor 1 says it doesn't really matter when you get a reward of 1. Whereas when a discount factor is less than 1, it says a reward in the future is worth less than a reward right now. And so to formalize the notion of what we mean by maximizing reward, we often talk about the discounted cumulative sum of rewards, which I've written down here. So that T indexes the time in an episode, and we're going to sum over all the rewards we get in that episode and multiply it by the discount factor to the power of T. This RT really just refers to this reward function here, evaluated on the state and the action you get at that particular time. Another way we can sort of visualize the Markov decision process is to think about this transition distribution. And on the right, I've drawn a deterministic transition distribution where the next state is just a deterministic function of the state and the action. So imagine you're at this state, this green state here. So the nodes of this graph are the states, and the vertices in this deterministic case are just actions. So from this green state, you have 2 actions, and you can take one of these 2 actions and go to a different state. And from there, and so on and so forth. And these edges will also be labeled by the reward function with the reward you get for executing it. Note also you can have, you can take an action, end it back up in the same state, and there can be loops as well and things like this. So what we want to do is, from any state really in here, particularly the initial states, we want to have a policy that tells us what action we should take so that as we traverse around this network of states, we're going to get the maximum cumulative reward according to this. In reality, though, we don't get given the Markov decision process. We're given some bits of it, and then we must deduce the rest through learning. So in general, we get given a set of actions, although in continuous control and very large action spaces, this is less likely. But for the purpose of this talk, all the action spaces are relatively small, and so we'll be given the set of actions. We'll be told you can move left, right, up, down, this kind of thing. The set of states is not given ahead of time before you interact with the environment, nor is the transition distribution, nor is the reward function. And the discount factor is a little bit funny. In the formal definition, usually you include it in the Markov decision process. But in reality, in RL, we treat it as a hyperparameter to try and improve performance. So in some sense, this is given. So what we see from this is a lot of the Markov decision process is not known ahead of time in RL, and yet there's very nice results that show that RL algorithms can converge the optimal policy, but usually there's a condition which is something like this, which says that if all it will converge if all actions are executed in all states repeatedly. For example, this is one of the conditions in Q-learning. So with that in mind, and the fact that we don't know everything, that leads us to the question of like, how should we move around this environment? On one hand, trying to maximize our cumulative sum of rewards, on the other hand, trying to find all these states, because there may be some state we've never got to and some action we've never taken that turns out to be very, very rewarding. And this is the exploration-exploitation trade-off that is often talked about. So here is sort of the most common universal exploration strategy that works unreasonably well in practice. And it's very, very simple. It says with some probability epsilon, because we know the set of actions, you can pick one of the actions at random. Otherwise, you just do the greedy best action you've got so far. And so this, this method for exploration dithers around the environment, and it eventually ensures, as you can see, because it's just doing random things at random times in random states, eventually it will ensure that all actions are indeed taken in all states and repeatedly. The only issue with this is that it can be very slow because the time taken to do this is exponential in the number of states and the number of actions in the worst case. You can construct environments where this is the case. And if we think about RL, remember there was, there are many other things we didn't know about the problem. And in fact, it kind of gets a bit worse from here. So typically when you think about what is a state, right? So we're not given a set of states up front. Often what we are given is an observation space. So if you think about the game of Go or Atari games, in Go, the observation space would be like the 19 by 19 board, and then each square on the board has one of three states. It's either empty, it's occupied by a black stone, or a white stone. And likewise in Atari games, typically what we do is we pre-process the image from the emulator into an 84 by 84 matrix, and then make it into grayscale bytes. So each element of this 84 by 84 matrix is 256 values. So then if you look at the size of the observation space, it is really quite large. So for Go, this is like 10 to the 172 possible configurations of this, of which most of them are actually legal. For Atari, there's a very large theoretical observation space. In reality, you see not many of those per game, but each game exercises like a different subset of that, and you don't know that ahead of time. There's already quite a large, so if we use just the observations, that's a very big state space to think about. And if we think about having to visit all possible states in terms of observations and take all actions, that's extremely large. That's going to take a very long time, more time than maybe we have, right? It gets a little bit more complicated when you start to think about history. And so history is really going to be one of the underlying ideas in this talk, because memory and history are sort of related, right? Your memory is your ability to remember the history. So maybe in Go, you don't need the history, or you don't need too much of it. It depends what you're trying to do. I think if you want to get the optimal policy in Go, you probably don't need the history because everything on the board tells you what you need to know. But if you want to, say, beat a particular player who has particular weaknesses, then the history of how that player has moved might help you understand the pattern of thinking that that player is exhibiting. So that might be useful. But for the optimal policy, probably not. In Atari, history certainly is useful. It's often the case that the actual observation space you see only contains part of the information you need to know. So usually it is, in many games, it is actually quite useful. And when you consider that, then in fact, that's another exponential growth that we see. So as the amount of history you require grows, it gets very large. And in fact, in the case of Atari, this can be really, really big. So if we take all of this into account and we define like a state space naively, we can see that there's a very, very large state space. And yet, if we want to find the optimal policy or get something that converges to it, we need to execute all actions in all states. And then if we combine that with the exponential time exploration that we see in epsilon greedy, things don't look good. This seems quite tricky. So what are we going to do? Well, in this talk, I'll propose three approaches to deal with this. The first is we'll propose a better algorithm than epsilon greedy, at least on some domains. And for the massive histories and the observations, I'll talk about an approach to summarizing these histories that works efficiently. And I'll also talk about how we can evaluate how well an agent can use these histories. I will also mention that most of the contributions here are in terms of their empirical evaluations. There's not theoretical justification for a lot of this stuff. It's really quite empirical, although intuitively I hope you can see the motivation for a lot of it. Okay, so first I'm going to talk about exploration. So the idea here is quite simple. We want to instill in an agent the behavior of coverage. And so this behavior is quite simple. It just says, I would like the agent to visit all states. That's all. That's just what we'd like the agent to do. That's the behavior we'd like it to exhibit. So for example, in this depiction of the state transition graph at the moment, we'd like to, and this stage, the current state is in green and the yellow states are visited. We'd essentially like the agent to then at least go around and color all of the states yellow, so it's visited everything. So how are we going to make an agent do this? Well, what we're going to do is we're going to introduce an incentive for the agent that asks it to revisit the fringe of what's known. So in this case, it's quite simple. These yellow states are really on the outskirts of what the agent had visited previously. And we're going to say we'd like the agent to visit more familiar states less often, or other way around, we'd like it to visit unfamiliar states more often. And the way we're going to do that is we're going to change the reward structure of the environment. So here's how we're going to do it. So if RT is the reward that our agent receives, we're going to take the reward that the environment would usually give us. So for example, in Atari games or in Go, this will be the change in the score or the state of the game. And then we're going to add to it an extra term, which will be intrinsically generated rewards. So this will be a reward function that the agent itself generates and does not come from the environment. There'll be a parameter that sort of tunes off between these two rewards because they won't exactly be on the same scale. And also sometimes we want to use more intrinsic reward than the environment reward and so forth. The intrinsically generated reward will be higher for state action pairs where we want to visit things more often because we expect that it's going to improve performance. So as we go through this, we're going to have to answer some questions. So one question is, what makes a good intrinsic reward for exploration? And in this work, we argue that there's basically two things. The first thing is we'd like the intrinsic reward to be high for rarely visited states. And we'd like it to decay to 0 over the lifetime of an agent. So for example, in this transition graph here, we'd like the intrinsic reward, let's say that these yellow nodes have not been regularly visited. We'd like to have a high reward for getting to those, so that from this initial state, the agent's incentivized to go to them, even if the environment doesn't give a reward for going there, or indeed gives a negative reward for going there. We'd like to somehow instill a different behavior to what the environment would like us to do. And we'd like it to decay to 0, because if the reward eventually disappears, then the idea is that the agent's kind of visited all the states and it knows what it can about the environment. And so then you can imagine thinking through it and formalizing this and saying, well, you visited all the states, you have an algorithm that is now operating on the original rewards of the environment. And so it should converge to the optimal policy of the original environment. That's why I want the rewards to decay to 0 eventually. However, there is a bit of a problem with this, which is if you think in a single episode, you're in this green square and then this green state, and you're incentivized to go to a state that you've been to before, you may end up going to this highlighted state here. Now, the issue with this state is it has a self loop. And in fact, it's relatively common in RL to have self loops. So if you've got an action that says do nothing, this will be a self loop. But also you can have things where you have cycles. So for example, there could be a state that you go to, and then there's another one you go to, and then you end back up. So this would in fact be incentivized to sort of travel around these three states continually, which is somewhat pathological behavior. So to remove that, we'd also like to encourage exploration across episodes, but we'd like to avoid repeated visits within a single episode. So once we've gone from this green state to this state here, we'd like to change the incentive so that it's not so attractive for this agent to revisit the same state again. We'd rather that it tried something else, like maybe it goes to this other state. And so to do that, and in fact, if it ends up in the cycle, by the way, we'd like to incentivize the agent to move away from that cycle, because that's not very useful either. And so to do that, we're going to have a part of the reward scheme that disincentivizes these loops. And so there are going to be two parts to what we're going to talk about here. So the first part will be a long-term novelty. This is random network distillation. This is actually a really nice work by the authors listed here from OpenAI and I think Edinburgh. And the idea is really, really, really nice. It's kind of the idea that you wish you'd come up with yourself. So you have two networks. One network is initialized at random, and it's going to take the observation that you get, and it will output a random vector because it's a random initialized network. This network will not change during training. There'll be a second network, which is a prediction network, and this will be learned during training. And the objective of this network is to mimic the random network. So every time you visit a state, you will train the prediction network to make its output closer to the random network. And so gradually over time, what will happen is that the prediction network's predictions will get closer to the random outputs of this other network. And then you can use the difference in these representations as a sign of novelty, because at initialization, the two networks will be very different because they're randomly initialized, but over time they'll converge on things that they've both observed, or rather the prediction network has observed and been trained to go towards in the random network. So it has this property that we wanted, which is initially things are novel and they have high novelty, and then it decays slowly over the lifetime of an agent. So if you think about a plot here of the novelty of a particular state, at the beginning, the novelty is high, and then gradually over time it decays. So for example, here, like maybe the agent's visiting the state repeatedly, so it's kind of training, and then it doesn't visit it for a while, so the novelty flatlines, and then it visits it, and the novelty decays, and then, you know, this is a neural network, so maybe there's some interference, right? And so it unlearns its familiarity, which causes it to start visiting it again, which means it starts to decay back down. This has some very nice properties, but it doesn't satisfy the second property we were talking about. The second property is to prevent this kind of looping around behavior. So here we're going to introduce a short-term novelty signal. And this is something we introduced that basically remembers specifics. So we're going to keep a non-parametric memory of seen controllable states. I'll say a bit more about what a controllable state is, but for now you can think of it as a notion of state that is related to the actions you take. So it mostly varies in a way, you know, it mostly captures features about the observation space that can be controlled by an action. And this will be important later. But it's, you know, you can think of it as a bunch of slots. So as you go through the environment, you embed your observation into some controllable state, and you're going to store it in a long list of things you've seen. And then when you want to calculate your novelty, your short-term novelty, you embed the current observation, you get a controllable state, you compare it to everything you've stored, and you pick, say, the top 30 of those, and you do a kernel density estimate of those. So you say, how novel is this particular state in the local neighborhood of things I've recently seen? And so that's going to give you a novelty signal. We're going to empty this buffer every few episodes, and so that will cause everything to be reset. So here's a similar graph to the previous one. Now for short-term novelty, look at the novelty of a single state. So initially for every state, the novelty is very high, and then as you observe it, it drops down. And then it fluctuates as you go through. So for example, in this period, you don't go to the state, but then you start visiting it again. Of course, this will go up and down to various degrees, depending on the neighborhood of the other things, the similar states that are nearby, but it will never decay. And so actually the total reward we're going to use is relatively straightforward. We're just going to multiply these two things together. So this is the whole sort of reward intrinsic generation system. We take in our observation, which would be like a screen from Atari. We're going to feed it through an R&D network, which will produce an alpha T, which will be a long-term novelty signal. And this will down modulate the novelty signal that's fluctuating quite a lot, coming from this episodic novelty part of the system. So the bottom part will change very rapidly because we just add in new states as we see them. The top part will change very slowly because it's trained by gradient descent. And so the idea is if we think about a novelty of a single individual state, it will start high, and then through an episode, it will go up and down, up and down, up and down, but gradually over time, it will decay. And of course, what's interesting is that what the novelty of this state is relative to all the other states, because all the other states will have different things going on depending on how frequently they've been visited or not. Okay, so question. Yes.
Can you define controllable state again?
I have not actually defined it, but actually that's a good question. Where did that go? Okay, so for controllable state, actually, let me just check where I am. I think I have it. Yes, it's coming up. If you can wait 2 minutes, I think I'll get there. But yeah, it's a great question. Maybe I should have mentioned it earlier. Thanks. Are there any other questions before I get to controllable state? Okay. All right, so we have these two systems. So one is slowly adapting, one is rapidly adapting. So this is going to get to what a controllable state is and sort of motivate it. One of the problems with novelty-based exploration is illustrated by this thought experiment. Imagine you have a room with a television in it showing continuously changing static, like on the right-hand side. The problem with this is it continually introduces novel states. So, you know, if you sort of motivate an agent to cover an entire environment and you've got something that's generating a lot of noise, that noise really, they really are different states. And so you should really be interested in those states and explore them. But I don't think this is desirable. So we're going to put this prior in. The interesting states are those that can be controlled. So what are we going to use for this? This is some very nice work from ICML 2017. It's again another very nice idea that we all, I'm sure, wished we thought of, and it's quite straightforward. Again, you take your original observation and you take the state that came out, sorry, the observation that came afterwards, and you put it through a Siamese network. And from the embeddings of these Siamese network, you classify what action mapped between these two states. And so the idea is that the representations you end up on, say, on the left-hand side, the state xt, contains mostly information about what tells you about the action for the next state. So the idea is that that's what's going to tell you what's controllable. I just want to check with the person who asked if that answers your question or if you've got a follow-up question. Perhaps not. All good. Okay. So here's a demonstration of this notion of controllable state, and sort of drawing out some of the differences between this and R&D and using random embeddings. So this is an environment we created called the disco maze, and as I play the video, you'll see why it's called the disco maze. So every episode, there's a completely different maze presented to the agent. So it's never seen this particular maze before. The agent is this green square, and around the agent, there's all these walls with different colors on them. Now, this environment has no rewards. So there's no task here for the agent to do. It is free to just sit still and do nothing. However, if it moves and it bangs into one of these walls, it will die and end the episode. So it should not touch the walls. It can sit still. So there's a strong incentive to do nothing, a very strong incentive. And if we look at the performance, for example, of say R&D on this, you'll see essentially its performance is 0. But when we use random embeddings, we start to see some fluctuation, some movement in this. And in this plot, the y-axis is the percentage of states explored. So how many different states does it get to, ignoring the different colors of these walls. So I'll play the video. And what you can see is that the walls are constantly changing color, and the agent is moving around. In fact, you'll notice that it does a kind of depth first search traversal of this maze, even though there's no rewards in the environment. And that's purely driven by this intrinsic motivation scheme that I just described to you. It's also not distracted by all these changing colors, because the colors don't help it predict what action it will take next. They're not correlated with it. So that's why, I guess for us, that was a good motivation of controllable states. And it's also a great way to see what the exploration will actually do in an environment, because it can just move around it and explore all the states. And it gets pretty good coverage. So this is almost 100% coverage, even though on all of these cases, it will be a maze it's never seen before. Okay. So from that, we thought, let's try it on some very difficult exploration problems. And in Atari, there have been a few games, about 6 of them, that have been very difficult exploration games. There's Gravidar, there's Montezuma's Revenge, Pitfall, and Private Eye, Solaris, and Venture. And in this table, we see the performance of a human on these levels. We also see the best baseline, which is roughly sort of the best agent score on these around the start of 2020, the start of this year's. And then this sort of scheme of rewards I've described is called Never Give Up, and that's at the bottom. So what you can see is it does pretty well, although there are some baselines that do better, although they're usually within sort of error bars of it or thereabouts. There's a few environments where it really shines. So for example, in Private Eye, it does extremely well. But most remarkably for us is Pitfall is a game that many people have tried to play for a long time. It's quite a nice game. I'll show a video of it later. But this is the first agent and the first scheme that seems to get off the ground in it. So we were pretty excited by this. And we were kind of wondering, is coverage all you need? Do you need to do anything else? So here is a scheme to sort of think about this. So you can pre-train your model with just coverage. So let's train it, as we did in the disco maze, we can train just using coverage and no environment rewards. This is kind of an unsupervised reinforcement learning phase. And so you learn to go around the environment motivated by just discovering things, not motivated by what the environment wants us to do. And then we'll transfer to a different downstream task. And in this case, what we'll do is there will be rewards in the environment, and we'll offer the agent that executes in this environment an extra action. And that extra action is to execute the coverage policy that it learned, which you can see here. So these orange lines here are meant to indicate that it decided for several steps to take the coverage policy behind this. We're going to use something called Easy Greedy, which uses levy flights to pick actions for longer extended periods of time, which allows you to get these long extended periods. Okay, so then what we did is we ran this on all 57 Atari games. This is coverage pre-training here. And there's a bunch of baselines and previous work people have done this kind of regime. And so we evaluate it with 0 rewards. And then we see what does the policy do when it's finally given rewards. What's interesting is it does extremely well. In fact, it's above human level performance on 27 of the games. And in fact, if you compare it to the original DQN that's given 200 million frames, it outperforms that, which is quite remarkable for us. And you might wonder, well, maybe this is just a very good prior for Atari. And that is kind of interesting to think about. We did some experiments where we took Atari games and we changed the reward schemes in them to be sparser or misleading. And we found that actually this kind of result still pulls through. So then we started to think about maybe we can actually get above human level performance on all Atari 57 games. It's a very long-standing benchmark in deep reinforcement learning, and no previous method has got above human level performance on all games. Particularly, almost all previous agents fail on the hard exploration tasks. And that seems to be where our exploration scheme really helps out. So here are 2 of the sort of harder games. Left-hand side is skiing, which is a bit surprising that it's really hard, because all you have to do is control this little skier to go through these flag posts. What makes this game really difficult is if you miss the red flag post at the end, all your work is for nothing. And that basically makes it very difficult to learn. Pitfall, though, has been one of the very difficult games. In this game, all you really need to do is you bounce around the screen until you find some gold that you can pick up. But there's very few rewards until you do that. So essentially, you move around for a very long time without getting rewarded, and mostly just dying, and then eventually find something. But it turns out coverage works really well. So what did we have to change from the reward scheme I told you previously to make it work better? There's basically 4 changes. Well, 3 changes plus use the coverage reward. So use the coverage reward we previously described with these 2 slow and fast novelty signals. We reparameterize the network so that we can basically deal with some issues with the noise in the gradients, the difference between the intrinsic and extrinsic rewards. One is sparse and one is dense. That's why it helps to reparameterize the network. We increased the backprop through time window. So actually we allowed the network to have more memory in the Atari games. That seemed to help. And then the final change is we allow each actor, so each part of our code that is executing actions on the environment to control the discount factor and this beta, this novelty trade-off per episode. So as a bandit to choose the best one as it goes along. And so if we do this, we get results like this. So on the right-hand side, this is mu0. Then we have R2D2, which is, I think, basically previous state-of-the-art on this. Then we have this never give up, which is this reward scheme I just described. And then we have Agent 57, which includes never give up. It's all built on top of R2D2, but it has a few more tweaks on top of it that I just described. What you can see is if you cap the mean score per game at 100%, it's 100%. It's greater than everything greater than human performance in all the games. But if you compare the actual average scores, actually it is a bit better than R2D2, but it's definitely worse than mu0. There's quite a big gap in the mean score, as there is in the median score. But when you look at the tail of the distribution of scores across all games, so this is the distribution over games, you can see it right at the bottom, the very hardest games, the ones where the score is the lowest. That's where really Agent 57 has shone compared to, for example, mu0. So mu0 is really focusing on a few games to get very good, well, not a few, but more than half of them to get really good scores. Whereas this agent is a bit more general, it's good across all of them. Okay, so I just want to end this section by saying coverage and novelty have been explored for a long time. We're certainly not the first people to do this. We've proposed a specific mechanism that seems to work really well with deep reinforcement learning. And we also demonstrated it works really well on hard exploration problems. There are other approaches that I think are pretty promising, and it's interesting to think how they might combine or extend some of this stuff. So, notions of uncertainty in both the value and the model that you're dealing with should play a role, like the learning signal or how much you learn really should be there somewhere, which isn't in novelty. There should be a commitment to a hypothesis. So thinking something like PSRL or Thompson, other Thompson sampling ways of thinking about this, or Levy flights seem important. But I also say that, still in Agent 57, we still use epsilon greedy. This is still a really good sort of heuristic that comes to save the day. Okay, so the next part of the talk is about getting allocentric memories of space from egocentric experiences. So in the previous work, we talked a little about controllable states. And I've sort of hinted that there is, you don't really want a one-to-one mapping between observations you're given by the environment and the state space that you act in. So in this work, we're going to think about how you might do this and what different ways you might, from this egocentric experience, might get allocentric memories. So in Atari, a lot of the observations are in kind of a flat space. There are a few three-dimensional games, but not many three-dimensional games in Atari, and they're not that rich. There isn't much RAM inside Atari, and the graphics is not strong enough to support very, very rich graphics. But in reality, we are subject to this. So probably, I think you're all sitting in a room most likely, and you have an egocentric view. So you get egocentric visual inputs. You don't see your room from the top down. You see it from your own body. But even though you receive this egocentric input, you have this allocentric sort of memory of the environment. This is work from a bunch of neuroscientists. It's very interesting. So no matter where you are, you can probably work out a few things. So there are going to be three sort of quantities or three representations we're going to talk about in this section. The first thing is going to be head direction. So where you're sitting, independent of how you turn your head, for example, roughly, not necessarily true north, but there is a notion of north. Like what's in front of you, and when you turn your head, that position is the same position. It doesn't change. So these will be head direction cells. And I will refer to like north, but remember the frame of reference is arbitrary. It's not like you have some magnetic reception, you get it true north, but there's an absolute frame of reference that's allocentric. Then also you'll have a notion of boundaries. So if you're in a room, there'll be some walls, and in particular, there's probably a wall behind you. And without looking, you probably have a really good notion of how far away that wall is. So there is some representation there of distance to the boundaries, and that's a pretty useful thing for us to know. If you close your eyes, you can sort of stumble around not too badly with this. And then you have another notion, which is inside the room that you're in, you'll have almost like a local GPS. These are place cells, and they will tell you your place in the room, right? And so you have these three quite useful spatial representations, but obviously you got them all from the visual input and vestibular input. So, the sort of egocentric velocities, so the accelerations that exerted on your cochlea, for example. And so how do you do that? That's kind of cool. And that would be quite useful for agents in three-dimensional environments. So here is a model that we've been working on that does actually exactly this. There are two parts. There's a visual pipeline and there's a memory pipeline. So the visual pipeline is this green thing at the bottom, and its role is it generates targets from visual inputs for the memory pipeline to predict. So it receives visual inputs, passes them through an autoencoder, and then much like we did with the short-term novelty signal, it then reactivates. So it looks over a bunch of slots of memories it's seen before and says, which of these previous memories I have of things I've seen are most similar to the one I'm looking at now. And in fact, it outputs a distribution over those. And then the memory part of the pipeline, the memory pipeline, is just fed egocentric velocities. So that's angular velocities and lateral velocities, but in a frame of reference that's relative to the agent. And from those, it's asked to predict a bunch of memories, a bunch of slots, and is asked to predict which one of those are reactivated. And it's trying to make sure that these slots here activate at the same time as the slots at the bottom. So let me unpack that a little bit. So as I said, the visual pipeline, we have a pre-trained autoencoder on the environment. We feed our observations through the autoencoder and end up with a feature vector. And then we store that feature vector in basically a ring buffer of previously seen things. And when we want to generate targets, we feed the observation through the autoencoder, get the feature vector, and then compare it to all the slots we had before to get the distribution over which ones are most similar. So the visual pipeline sets the targets. And although there's an arrow here, the information that's flowing from the visual pipeline into the memory part of the system is very limited. It's really just like which of these slots is active. The memory pipeline consists of 3 recurrent neural networks. Each of the recurrent neural networks has a different velocity as input. In fact, one of them has no velocity inputs. Another one has just lateral velocities, and the other has both of them. Each of these recurrent neural networks must predict which of these slots will be active at the next time step. These slots, so each RNN has its own set of slots, and these slots store previous hidden states of these recurrent neural networks. So really it's trying to say, output a prediction that looks like a previous state of this recurrent neural network. And so that putting it all back together, hopefully it makes a bit more sense because there's a few interacting parts. So the visual pipeline generates these soft targets. So it generates a distribution over these slots, and then each recurrent neural network in the memory pipeline is asked to essentially predict that distribution over slots, but using an impoverished source of information. It's only really told velocities, or in one case, nothing, but it's also given corrections. So once it's made a prediction, then there's a correction phase. So what happens in this phase, we do the usual forward pass. You get a distribution over which of these slots is active. That's given by this softmax distribution here. And then the correction is fed back to all these recurrent neural networks in the form of a weighted sum by this attention over the visual memories. But note, this is basically a one-dimensional object. It's a scalar. So the actual visual input never really goes back, just which slot is active. So we get a weighted sum, so attention over the memories for that recurrent neural network. So recurrent neural network 1 has a ring buffer of memories, which are activations of this recurrent neural network. And as a correction, it will get a weighted sum over all of those slots that's previously output. That's the only information it gets from the visual system. Let's try and fix it up. Okay, so that was the architecture. And now I'm going to talk about visualizing some of these things and how this connects to some of these results in neuroscience. So in this slide, I want to talk a little bit about the problem setup and also introduce this notion of rate maps in case you're not familiar with it. So typically in rodents, where these experiments are often done, they use quite simple shaped environments. For example, the square environment here. And so that's what we're going to use here because they'll also shape the rate maps we look at. So we have a square environment like this, but the actual input, the view of the agent will receive is a bit like these ones at the bottom. So there's some objects in the distance to try and help the agent sort of locate itself. And then there's white walls that denote the boundary and some pattern on the ground. And what we're going to do is we're going to visualize different parts of this memory pipeline. And in particular, we're going to look at specific hidden units or predictions of this. And we're going to plot the magnitude of those predictions relative to where the agent actually is inside this box environment. So for example, this rate map here is the same size as this square. There's a top-down view. And what we're saying is for this particular unit in the neural network you're looking at, it is most active in this position, which would be roughly here in the square. And that was derived from this visual input, right? So you can think of this as like the local GPS. This is like the place cell representation we talked about previously. This image here occurs in one of these corners. And from this rate map, we're saying that the part of this, there exists a unit in this memory pipeline that is most active when the agent is in this corner, which is what this is. Okay. So here are some actual recordings from rodents, I believe, of these actual rate maps that you see in real animals. So the way to read these things are very much like the rate maps I showed previously. So the first row are head direction cells. So this head direction cell, the frame of reference here is absolute. It's not a relative position. So this basically answers, this says the rodent believes it's facing east. Or rather, the rodent has a representation that correlates with it facing east. This one says the rodent has a representation facing west, north, and so on and so forth. And there's usually pretty good coverage. So I can only show like a few of these on the slide, but there's many of these cells, and they cover the whole. They form a basis over all of head direction. Then we have ego boundary vector cells, which are depicted here, and these sort of are the intermingling of head direction and where distance to a wall or something like that. Is there a wall? So the way to think about these ego boundary vector cells is they really answer the question: is there a wall on my right? So they're not completely allocentric, but they're quite important actually. Then we have boundary vector cells, and these cells are a little easier to read. So, for example, this cell on the left, this is most active when there is a wall on the east. This one is active when there's a wall on the south, and this one is a wall on the north. In particular, when the rodent is close to these. So remember, the way to read these rate maps is that we're registering the cell activity when the rodent is in that XY position on the map. And finally, there are these place cells. And these place cells are essentially, where am I in absolute coordinates? So they are like the local GPS. And as you can see here, from this rodent, they're able to decode cells that activate when the rodent is in different particular positions in this environment. Okay. So we recover basically these four things in our neural network. So here are some rate maps from this spatial memory pipeline. We get head direction cells, and as you can see, they look very much like the rate maps I just presented. We get ego boundary vector cells. These are plotted in a slightly different way, but essentially each of these quadrants corresponds to a particular direction that the rodent's facing in. We get boundary vector cells. So for example, here you can see boundary vector cell that's selecting a wall in the north, a wall in the east, a wall in the middle, a wall in the south, and a wall in the west. And then we also get place cells, which tells us the absolute position. So you can see there's various positions here. Okay, so what's the use of that? Well, now we can start putting into agents. So there are some nice tasks, and I'll talk about some more in a little bit. Nice tasks to sort of evaluate this. And a classic task actually done with rodents is called the Morris water maze. And the way that works is the following. The rodent starts at some position S at the beginning of an episode. And then the rodent's allowed to freely wander around the environment, and there's an invisible goal. And when the rodent discovers that invisible goal, they receive a reward, and then they are picked up and moved to some other random location. And the test is, how quickly can the rodent go back to the goal that's invisible from a new location? So they're given some time budget, and they can repeat this many, many times. And the more they do it, the more rewarding they get. So neural networks can do this. This has been shown previously. What's interesting for us is because we've sort of separated this notion of space from the visual appearance, how does this affect generalization? And in particular, can we transfer to visually distinct environments? So we're going to train in a bunch of environments, and then we're going to evaluate in a very different looking but same structured environment. And we're going to test how quickly the agent is able to adapt to this new environment. So here's the result. The black line corresponds to an agent with no spatial memory pipeline. And the solid black line, which you can see here, is the original training performance. And then when we go to the novel environment, you can see essentially, okay, maybe it learns a little bit slower, but it's roughly the same. I'd say it's roughly the same performance because there's a lot of noise in RL in general. So they both solved the task, and they both solved it at roughly the same speed. The red solid line is the training performance of the spatial memory pipeline. And as you can see, it's a little bit faster. But what's most remarkable here is when we transfer to this new, completely different environment, but having pre-trained on a bunch of similar environments, there's a very rapid acquisition of solving this task, of going back to the goal it's seen before. In fact, it gets really good above human level performance in very few experiences. So that seems very nice. One question you might have is what happens if you change the shape of the environment? And so we pre-train in a bunch of square environments and move to a cross layout. So these screens, by the way, give you an idea of how visually different these tasks look. You can see they're quite different. And what we see there is if you train from scratch, we have this black line here, but when you transfer, you get very rapid transfer to this new shaped environment. Okay, so we've sort of seen some examples now of where memory can help and different kinds of memory that pop up and the things it can do. So how can we start to think about like a more holistic view of like how do you test memory in agents? Well, fortunately, people have thought about memory for a very long time. And so here's a sort of a picture of different kinds of memory that people have thought about in psychology and neuroscience. I mean, this is just a taxonomy I threw together. It's certainly not definitive, and there's certainly things missing from it. But there's a few ways you can think about what's going on. So you can think about short-term memory and long-term memory. And there's different kinds there. So for example, if I ask you to add the numbers from 1 to 100, you'll probably use your working memory to work it out. And your sensory memory is what you sort of use to put a coherent view of all the sensory information your brain receives together. But then, and those are quite short term, so they'll disappear, you know, varying timescales, and it's not an absolute distinction between short and long term, but maybe a few minutes or seconds, something like this. And then long-term memory can last, you know, hours, lifetime sort of thing. And there's maybe two different kinds of long-term memory. There's sort of very explicit things. So if I asked you what the capital of Norway was, you can probably tell me that, hopefully. But equally, if I asked you, so episodic memory would be something like this. You probably had breakfast this morning, or at least a drink of some sort. And you can probably remember even now having done that, right? So sort of revisiting that, imagining maybe who you were with, or maybe what was on the table, or where you were. All of that would be an episodic memory. And then to think about what an implicit memory would be, there'd be something procedural. So for example, you can probably make a cup of tea or coffee, but you probably can't remember the first time you did it, unless something really weird happens. So, those are just different kinds of memory. And you can see there's quite a lot of variety in the things that you want to do there. So what we thought is, let's make a collection of tasks to sort of try out the memory our agents have and see where the weaknesses are. And so that's what we did. We came up with, we basically put together a bunch of tasks, some of which we came up with. They're challenging for humans, but humans can do them all. And they're also really challenging for agents, and agents can't do all of them. So I'm going to show you some examples. So these are some psychology tests that people use. And the basic idea is you're shown like an image, and then you're shown a color which says you should look at this when you see this image. And so this is like the training phase, and then you're shown the image and you should look up, right? And you repeated this with many different things, and then they get mixed together. So it gets progressively harder. So this is called the arbitrary visual motor mapping, because you're mapping from some arbitrary image onto a motor control, which is look the left down, upright. Another task is change detection, which does kind of what it says like on the box. You're shown sort of an image, and here we can see like a backwards E. And then you're shown a new screen, and you're asked, is it the same or different? So if it's the same, you should look at the left. If it's different, you should look at the right. And hopefully whoever's doing this, okay, it's the other way around. It's the same, so you should look to the right. Okay, so these are two sort of psychology tests. Another test is spot the difference. So in this task, there are two rooms. In one room, there are a bunch of colored buildings. So you can see here, there's like two blue, a black, green, and a transparent one. And so you're allowed to sort of look at them for a while and try and remember all of them, which the person here is trying to do. And then after some amount of time, you're going to, because you get no reward for this, there's no reward for looking around. Then after a short period of time, you're going to be asked, you're allowed to go to the next room, and you can't go back. And then here you must go to one of these blocks that's different from the previous, and of course it's this one. Okay, so that's called spot the difference. And then there's another task which is goal navigation. This is a bit like the Morris water maze task, except the goal is visual. So you can see as you go through, it's quite a visually rich environment. There's lots of cues around of things you can remember and places you can remember being. And as you go through, eventually the agent, or I think this is actually a human playing this, will find the goal. The goal is here, and they'll walk towards the goal, and then they'll get respawned, and they have to get back here as quickly as possible. Okay, that's that one. And then finally, this one is quite challenging, is called transitive inference. So there's a sequence of objects, and they have an order between them that you don't know. And the agent's presented with pairs of them, and the pairs delineate, say, in this case, like yellow is greater than blue. And you're given disjoint pairs, usually adjacent pairs, and then you're queried on pairs that are further apart. So for example, you might be told that orange is less than yellow, yellow is less than blue, and you're asked, is blue greater than orange? And you have to choose which one to go to. So it gets this notion of transitivity in a relationship between these colored objects. Okay. Another sort of important aspect of reinforcement learning and evaluating it is a notion of generalization. And so in this work, we looked at generalization in 2 dimensions. So as we saw with the memory work previously, where we're going to visually distinct environments, the stimulus can have quite an effect on how memory is used. And so we have 2 different sets of stimuli for each of these environments, a training set and a holdout set. So for example, these will be different colors, and some of these colors you've never seen before at test time, but you're trained on a different set. But of course, for memory, one of the key dimensions of variability is the time length. As I showed before, this is a common way of splitting up different kinds of memory. And so in this particular case, we're going to split up the scale of a task into 4 boxes: small, medium, large, and extra large. We're going to train on small and large tasks, and then we're going to evaluate on medium and extra large. And we're going to call this interpolation, which is where you're between small and large, and extrapolation, where you're evaluating on large environments. The idea is that there's no sort of even larger set of examples that you can interpolate between. Okay, so that's what we're going to look at. We're going to report performance of various agents on train, interpolation, and extrapolation, and on a wide range of about 12 memory tasks. So, I mean, no paper on this would be complete without proposing an agent for this. And this is an agent that we essentially co-evolved with these tasks. So we sort of looked at the tasks, looked where agents were failing, and then we worked out what was necessary to solve as many of the tasks as possible. It has a few components. It has a working memory, which is really an LSTM. It has an episodic memory, which is one of these slot-based memories that just records all the things that have been seen before and is made available to the network as it goes through. And there's also an auxiliary task, a contrastive predictive coding loss, that helps regularize these representations and ensure the right information is recorded. So here's the evaluation. As I mentioned, there's training performance, interpolation performance, and extrapolation performance. And we did a lot of ablations. I've included 3 ablations here that I think are quite interesting. So apologies, the text might be a bit small, but essentially we've got an agent with an LSTM, an agent with an LSTM and CPC, because it's contrastive predictive coding, an agent with LSTM plus episodic memory, and then the full agent, this memory recall agent that has all the components together. So from what I said, it should come as no surprise that essentially this agent with everything does better than the others. It's also interesting to note that training performance is, of course, better than interpolation performance, and that's actually better than extrapolation performance. But maybe what's quite interesting here is which tasks prove to be difficult. So this arbitrary visuomotor mapping task, once you have some notion of an episodic memory in it, actually this is not too difficult. For train, interpolation, or extrapolation, you can see the scores are all quite high. But if you don't have this episodic memory, then it's quite difficult actually. And that's also true, I think, for some of these continuous recognition tasks, which I didn't really talk about. But what's really proved to be really difficult is spot the difference tasks. So spotting how things are moving around, for example. So there's a spot the difference task where things move around differently, and you have to identify those. Those proved to be particularly difficult, and extrapolation, anything to do with spot the difference, was very difficult. So it's not completely solved, but hopefully this sort of illustrates the kinds of things agents struggle with if you don't have various components. And it's still spot the difference is something that haunts me at night. Why can't we solve this? Anyway, okay, so with that, I'd like to summarize. So the talk, we started off by thinking about short and long-term novelty and how this can motivate a kind of coverage behavior and how this is good for exploration. We saw that if you predict the reoccurrence of previous egocentric experiences, then you can get all of these very nice allocentric representations you see in neuroscience, and actually these help agents generalize to novel stimuli, both in terms of the topology and the visual appearance of the environment. And finally, we talked about how classic tasks from psychology can really sort of torture these neural networks and show us which components we need to get good memory. And we found that LSTMs or slot-based memories are pretty good for generalization, especially when you combine with auxiliary tasks. And with that, I'm done. I'm happy to answer any questions.
Thanks, Charles. We have time for a few questions. You can unmute yourself and ask the question.
Hi, very nice talk, Thomas Sandholm. So I had kind of two questions, not really specifically about this work, but in general. So one was in these games, how many training playthroughs do you actually need? And I know it's kind of a different question for different ones of these games, but what order of magnitude?
Okay, that's a great question. It's also a troubling question for us because we'd like it to be as small as possible. So to get all 57 games, we needed about 10 to the 9 frames. It's a lot. It's order of that.
Total?
Yes.
Or per game?
Yeah, per game. Yeah, that's a lot of frames.
But that's not so bad. That's just 1 billion. That's not too bad. I thought it would have been more.
Well, let me make sure.
It's,
I have
it's actually frames. It's not playthroughs. It's frames.
It's frames, yeah. So it's order of that. It might be like 10 to the 10, something like this. It's roughly that order of magnitude. It's like billions of frames. I guess, but that's not true for all games. Some games you can get really good performance much quicker. The reason we have to go for so long is actually skiing is what takes the longest. So it's not a very complicated game. It's one where you just have to go through the flag posts, but the credit assignment is really poor.
Yeah.
So I think the reason actually we're not a lot faster in all of this is because the credit assignment algorithms we have are not really good at backward assigning why certain things happen. So essentially what happens in skiing is you get to the bottom of the slope, and if you don't go through the last 2 red flags, you get no reward. And so working out why that is something that algorithms really struggle with. And for us, it's really simple. Like you'd be surprised if I told you a priori that skiing was the hardest game, but it turns out it is in terms of data efficiency. Yeah.
So in terms of playthroughs, how many playthroughs is that?
Well, it depends on the game, but most games are around, let's say, 1,000 frames, something like this. So,
Okay, only 1 million playthroughs.
Something like this. Yeah.
Wow. Okay, that's cool. And the other question I had is that there's been some people observed that in Atari games, at least some of the Atari games, you don't have to actually look at the state. Like you can just string together a sequence of actions and play extremely well. That it looks like you're shooting at something, but you're just shooting because you know it's not in that direction, because you know now that it's time to shoot in that direction and stuff like that. Do you have any comments on that? Because for those things, it seems like there's no memory needed. You could just stretch together a sequence of actions well timed.
Yes. Okay. Oh, by the way, I just found my slide. So sorry, the total number of frames would be like more like, it looks like, 10 to the 10 is about right. Yes. So in terms of this action, like just memorizing the actions, so first of all, when we evaluate, we use random no-ops. So we insert a random number of no-op actions at the beginning of the game to try and alleviate some of this effect. This is like, I think this is the brute, like Mark and Joel tried out. So we insert random no-ops. We've also evaluated, but it's not included in the work we put out just yet, on sticky actions. So this is the idea where at some point, at random, actions will kind of stay held down for a while, which is another way to sort of alleviate this brute sort of setup. And things seem to work out pretty well there as well. There's a few changes we have to make to the memory, but it also works out there just fine.
And without those, is it like all of the Atari games are easy, or is it just some of them?
It's just some of them. So I don't think it's all of them. But I think also you've got to look at the amount of, basically it scales in the branching factor. So the more actions you have, the harder it is. So something like Pong, where you just move a baton up and down, that's not too difficult, or Freeway, where you just need to press the up arrow. But more like richer games like Montezuma's Revenge is really a function of memory, because what you're doing with most of those methods is you're just kind of distilling the entire search tree through the game with the actions into memory. So you require a great deal of memory, and that's really the factor that makes it difficult for some versus others. Yeah.
Okay, cool. Thank you.
Thank you.
Another question. We have time for 1, 2. I mean, depends on Charles' schedule next, for sure. All right. I think there are no more questions today. Maybe people are heading off for Thanksgiving. So maybe you should thank the speaker once again. Thanks, Charles.
Thanks very much. All right. Cheers. Thanks, Ish.